Welcome back, guys, and I do hope you and your family are keeping really well at this time. So, we've been looking at different types of energy, and I want to finally put together two types of energy mathematically. Okay, so I want to look at gravitational potential energy, and I want to look at kinetic energy. And what I normally do in class is I take this big nut here and I lift it up and give it gravitational potential energy. I think I can do this actually without breaking the camera. And then I just let it go. Okay, so it hits the floor. It's made a dent in the floor. No, never mind. And it speeds up and speeds up and speeds up as it falls. Okay, so it's changed its gravitational potential energy to kinetic energy. Okay, so on a small scale with a little one, gravitational potential, kinetic getting bigger and bigger, and the kinetic energy is maximum just before it hits the desk. Okay, the velocity is going to be fastest just before it hits the desk. It didn't reach its terminal velocity by any means. Okay, and we can work out how much gravitational potential energy it had, mgh, and just before it hit the desk, it will have converted all of that gravitational potential energy to kinetic, half mv squared, and we can work out what speed it will be doing, what velocity it will be doing when it hits the desk. This is called the impact velocity, and it's quite a tricky little calculation. Once it's hit the desk, heat and sound. Okay, would you believe it? When it hits the desk, it actually gets a little bit warmer. And there are experiments where you drop something and drop it and drop it and drop it and drop it hundreds of times, and you can actually feel the material getting warmer as you do that. So, just to summarise before we go up to the board, okay, we're going to look at gravitational potential turning into kinetic, the kinetic energy being maximum just before it hits the surface, and we're going to use our energy maths to work out how fast it hits the ground at. This is called the impact velocity. And I'll just tell you a little story from school. When I was a kid, I just didn't get this. Impact velocity, well, surely it's zero, yeah? If it hits the surface, it must be going at no speed at all. What do you mean about the impact velocity? No. What I hadn't got in my head was the impact velocity is the speed that it goes crashing into the surface at. And that's going to be its maximum speed because it's converted all of its gravitational potential energy all into kinetic. So it's a big store of kinetic energy, so it must be going really fast. So let's go up to the board and see if we can work out how fast something that's dropped will hit a surface. Its impact velocity. Okay, so this is going to get a bit tricky now. We're going to look at impact velocity. So what we're going to do is we're going to put the equations for gravitational potential energy and kinetic energy together. Impact velocity, the way to get your head around it is to go back to our idea of something being lifted through a vertical height, okay? And we'll put the object here, okay, and it has a mass, and up at the top it has lots of gravitational potential energy, okay, and remember that we abbreviate that to E with a little p below it, okay, and if it falls off the slope, it's going to hit the ground, okay. And when it hits the ground, just as it hits the ground, it's going to have the maximum velocity. So here, it's going to have maximum kinetic energy. So what it's done is it's converted all the gravitational potential energy that it had up here. It's converted all of that into kinetic energy. Okay, now we're going to assume that this is 100% efficient, of course, that it doesn't lose any energy rubbing against the air and things like that. But for a small fall, it's a pretty good sort of assumption. So it gained gravitational potential energy, and then it lost that gravitational potential energy by falling and hitting the ground. And when it hits the ground, all of the gravitational potential energy will have converted to kinetic energy. So the amount of gravitational potential energy it had is now all kinetic, so we can say that. So let's take this a little bit further now. Okay, so here goes, and it's a tricky one to follow this, so you might want to pause the video a few times, and I do understand if you don't quite get it. This is, it's quite high level stuff we're going to do here. In fact, I do a similar or the same calculation in the early stages of A level. Okay, this is the bit you should remember, that potential energy is mgh, and if all that potential energy converts into kinetic energy, it's going to turn into a half mv squared. Okay, now some of you know I mentioned these moments, spine-chilling moments in physics when you teach, and writing that is a really special moment because you look at it and if you're mathematical you go, what? Okay, there's an m on this side of the equation and there's an m on that side of the equation. So, I don't like saying the m's cancel, but if we move this m, which is the same mass, this one, to this side of the equation, we get m divided by m, and they, I don't like to say cancel, they become the number 1, so they're gone. So, divide this by m, and we get gh equals a half v squared. Okay, so what's spine chilling about that, you might say? Well, what it means is that the speed that you hit the ground at, this is really strange, the speed you hit the ground at doesn't depend on your mass, okay? So, don't do it, but if a light person was to jump off a building and a heavy person jumped off the building from the same height, they could hold hands on the way down, okay? They would both accelerate at the same rate and they would both hit the ground at the same velocity, okay? Isn't that weird? It's kind of not what you'd expect. The heavier person would have the same impact velocity as the lighter person. Just not what you'd think at all. Okay. And some of you might have heard the apocryphal story of Galileo having this bet with his mates and saying, what happens if I drop a small light ball bearing and a heavy large cannonball off the Leaning Tower of Pisa? Been there, been up to the top and had a look at it. They would both fall at the same rate and they would both hit the ground at the same speed. Okay, there's no mass in this impact velocity equation. Okay, so we want the impact velocity v. So we've got a half here, so let's double this side. So we'll double this side, 2gh is equal to v squared. And finally, let's square root to get v. And I'll swap sides of both. So square root of v squared is v, and it will be root 2gh, so the impact velocity will be equal to the square root of 2gh, root 2gh. Okay, not something you need to memorize, but I think it's good maths and it's good to do this calculation so you can see how we equate gravitational potential energy to kinetic energy, and we end up with a formula that gives us the impact velocity for anything at all that you drop in a gravitational field from a vertical height, neglecting air resistance. Okay, so this doesn't take into account air resistance, and unless you're dropping a feather or a piece of paper, if you're dropping something in the laboratory or off a shelf or something, this equation is going to work every time. So finally, let's put this equation to use. So let's put some numbers on this. So mass doesn't matter, it's not in the equation. Okay, so let's have a height here. Okay, and let's make that 5 meters, 5.0 meters. Okay, hope that's clear. I put a decimal point in there. Okay, 500 centimeters, but we never do it in centimeters, so 5 meters. Okay, we know the gravitational field strength G is on Earth approximately 10 newtons per kilogram, so we can put some numbers into this. V will be root 2 times the gravitational field strength 10 times the height that we lift through 5. Okay, so let's just quickly work that out. So 10 times 5 is 50. 50 times 2 is 100, and the square root of 100 is 10. So V, the impact velocity, will be 10 units meters per second. Okay, so a good look there at how we equate gravitational and kinetic energy and how we derive the formula for impact velocity, a bit advanced for GCSE, but it's good stuff to practice. And finally, putting some numbers into this equation. So I do hope that video was useful, and the other ones I've done on elastic strain energy, kinetic energy and gravitational potential energy on their own. It's a complicated little topic, so I hope you can get your head around the formulae, but I do hope you got something out of this video and you feel a bit more confident at dealing with the equations for gravitational potential and kinetic energy. Anyway, I'll be making some more videos soon. Look forward to seeing you then.